Hi, my name is Eric Chu. The co-author of this paper is Dr. Nicole Okamoto and Dr. Sadie. Um, we are all from the Department of Mechanical Engineering at San Jose State University in San Jose, California. And this paper is going to be about startup power requirement for an axial groove thermosyphon. This scope of this project is to determine the minimum power requirement to begin the thermosyphon heat transfer process of a axial groove ammonia filled thermosyphon heat pipe. And we tested this thermosyphon heat pipe at different tilt angles and different saturation temperature. This thermosyphon was provided by Spaces and L'Oreal. They are a telecom satellite company based in Palo Alto, California. The overall geometry of this thermosyphon looks similar to this. It is made from a T6 6061 aluminum, and it has 39.4 gram of anhydrous ammonia as its working fluid. And the minimum power requirement to begin the thermosyphon heat transfer process is something like this. If there's not enough heat transfer, it will be conducting heat in a conduction mode, similar to the picture on the left. And once there's enough heat going into the evaporator, the thermosyphon process begins and the fluid start boiling inside the thermosyphon. And our test setup looks something like this. Heat is being applied at one end and heat is extracted at the other end at the condenser. And the data logger takes temperature throughout the testing apparatus, and it's constantly being logged from a computer connected to the data logger. And here are some of the methodology that we looked into: the heater assembly, the cold plate assembly, the mechanical retention system, the heat loss measurement, and look into the boiling surface of the internal axial grooves and how nucleate boiling dictates the temperature difference at the boiling surface, and also the temperature measurement uncertainties and how this startup behavior looks like. And we analyze the results at the last section. And our heater assembly looks something like this. It's made of copper, and it has a FR4 backing plate forcing the heat through the copper as a heat spreader. And we have 7 heaters that all sandwiched together with some thermal gap pad. And electrically they are connected in a parallel configuration. And the heaters are being driven with a DC power supply, and the data logger collects the current and voltage of the heating elements. And coolant is being sent to the cold plate, and this multi-pass heat exchanger cold plate that we built for this project. And the cold plate and the heater blocks were all sandwiched together with this mechanical retention system that's made out of aluminum and some Delrin and FR4. And it does its job pretty good. It compressed the gap filler pretty evenly, as seen from the picture. And we ran some heat loss analysis on this testing apparatus. There's airflow flowing in the test station continuously. We use XPS foam, extruded polystyrene foam, to blanket the testing apparatus from too much heat loss. And this is the overall thermal resistant network. And we're interested in the loss at the evaporator and the adiabatic section. And here are the heat loss equation that we used. And the physical measurement looks something like this. The thermal resistance was measured to be about 4 degrees C per watt. And we also ran some CFD analysis using COMSOL multiphysics. We used a K epsilon turbulent model, provided 40 CFM, and the mesh was 250,000 elements. And we use the same material properties on the XPS foam as the heat loss measurement. And the results were very similar. Thermal resistance was measured to be around 4 degrees C per watt in the CFD model. And this is this physical versus CFD model heat loss measurement. They are almost the same. The results overlap each other pretty good. And the overall thermal conductivity is measured using the heat pipe length from the center of the condenser flange to the evaporator flange. And we looked into the flooded surface of the evaporator. And this is how the heat pipe's internal geometry looks like. And these are the equation that we use to determine the saturated fluid level and vapor volume. And we can see that as the saturated temperature changes, the fluid level change as well due to the change in its specific gravity of the fluid. And with some visual aid, we can see that 60 degrees Celsius in this vertical orientation, the saturated fluid is decreasing as temperature decrease. And the tilt angle also affect is how the evaporator is flooded. As you can see, as the tilt angle decreases, the evaporator become less flooded. And nucleate boiling. So this is a nucleate boiling graph pulled from the textbook, heat transfer textbook. This represents water. Nucleate boiling, water will see 10 to 30 degrees Celsius of excess temperature. But for our case, it's ammonia as working fluid. And this is the nucleate boiling equation. And we can see the viscosity and the surface tension decreases as temperature increase, as saturation temperature increase. And as saturation temperature increases, the fluid property decreases and the T-axis will increase if the heat flux is constant. And we took a standard calibration procedure for the thermocouples. And we install thermocouples over the body of the heat pipe. And these are some sample startup character of the thermosyphon at 1870, 155, and 270 watts. And as you can see, 18 watt startup, the heat flux is smaller, so the excess temperature is smaller. And as power was increased to 70 watt, the temperature startup increased, similar to 155 watt to 170 watt. And the result that we found, as the tilt angle decrease, the boiling surface area would also decrease, and the heat flux will increase due to the surface area being decreased. Therefore, higher excess temperature is present, which result in a lower overall thermal conductivity. And our test result agrees with the nucleate boiling equation, as the saturation temperature increases, the fluid property changes, and it leads to a higher startup temperature, higher excess surface temperature. And as we change the tilt angle and the saturation temperature, we have recorded about 3.5 watt of power in order to initiate the thermosyphon process. And as we can see the data, there's a dip between 60 and 70 degrees tilt angle in two of the saturation temperatures. That is probably due to heat loss measurement errors, which gave us a more errors power reading. And we were successfully able to capture the temperature difference to initiate the thermosyphon process. And we were not able to recognize the trend of minimum startup. This is probably due to the error on the heat loss measurement due to fluctuation of the ambient temperature. Some of the future plans for this project is to improve the heat loss measurement model and add more temperature measurement points at different location of the thermosyphon heat pipe. And maybe we can eliminate the overall heat loss from this experiment by running this experiment in vacuum. Special thanks to Space System Laurel for providing the thermosyphon. Thanks to San Jose State University for the opportunity to work on this project.